Hey, welcome to assignment 8. So here it's time for us to talk conceptually. We saw in the 7 in class video that we could build a graph of position by integrating our velocity function. And we did that in every step. And what I remember seeing there was that as we added our next sliver of area to the area that had already been accumulated, this amount of added area under the velocity curve turned into a change in y values on the position curve. So displacement was equal to that integral, that area under the curve. Well, today I sort of want to be both more explicit about a connection like that. I definitely want to move it away from you just thinking about that relationship with velocity and position, because it works with any derivative and its antiderivative. And we're going to be saying a whole lot of things that aren't position and velocity. So let's have a little thought moment. Let's imagine that I have a fixed curve, just whatever, f of t, okay? And I even have a fixed starting point, x equals a. Okay? I'm going to start here. And what I want to know is what I really want to do here is build a formula called the area under the curve formula. Okay? Area under the curve formula. Now, remember, this is now a constant. Not going to change. It's some fixed number. And the curve is a constant. Now, I don't mean that the curve has the same y value at every point. No, I don't mean that at all. What I mean is that I'm not changing the curve from moment to moment. And you might think, oh God, why would you ever even think about doing that? That's horrible. That's like killing baby ducks or something. Stop it. But no, we really need to be clear that this is being held constant. It does have different y values, but I'm not changing from this curve here, and then I move over my next increment, and now I have an ln curve. And then I move over my next increment, and now I have an x to the third curve. And I move over my next increment, and I have a sine curve. We're not doing that. And because we're not changing curves from moment to moment, I'm holding that as a constant. That's fixed. That's not changing. Okay? Now, with these two constants, I'd like to create an area under the curve formula. So what does the area under the curve formula require? What do we need? We've got this constant. We've got this being held constant. So then what does the area under the curve actually depend on if these two things are fixed? What do you see? I see that if I stop here, then the area of the curve depends on what? If I keep going, the area of the curve depends on what? If I keep going, the area under the curve from that fixed starting point with this fixed curve depends on what? Exactly. It depends on how far over I go. And so when I think about this area, I think about integral from a to where I stop, x, for f of t dt. Now, this is a dummy variable. It doesn't matter what the variable is, because this is being held constant. What determines the area under this curve is simply how far over I go. Okay? This is a function area under the curve as a function of how far over I go. And in general, what I'd like to say is this area under the curve function. What I'd like to say is that I'm going to call this big F. Big F is the area under the curve function. Okay? Okay. See, look. Big F, the area under the curve, is a function of x, how far over we go. All right. Fabulous. So that's step one. Step two. Wait, there's more. By definition, big F of x, that's the area under the curve function. By definition, we know that big F prime is going to be the limit as delta x heads to 0 of delta F over delta x. Okay? Right? This is our slope formula, and this is saying let the 2 points be infinitely close to each other. Right? We want the distance between the points to head to 0. This is that change in y values. This is that change in x values. This is just the slope formula with the distance between the 2 points heading to 0. And so we know, yeah, that's what derivative means. Well, let's take this understanding a little further. Okay? Let's understand that that delta F is in fact the change, remember from the 7B, I'm sorry, the 7 in class video, that the change in F, did I want to say that? No, it's a big F. There we go. The change in F equals F of B minus F of A. All right? And so I'm thinking now about this, I'm thinking still about this delta F. And I'm thinking that one way we understood it was to say that change in area from where we were to adding that next sliver turned out to be a change in y values on this antiderivative function. In the 7 in class, this would be S of B minus S of A. A change in y values on position was this change in area. And so now I'm thinking about delta F this other way. I know, Mr. Cooper, why you were thinking about it that way just now. Why have you changed your mind? Well, F of x times delta x. So this is this. It's the area of a rectangle. This is our subinterval width. There's our subinterval width. And this is our height. You know, the height at some point. So I'm getting my change in F to be this as well. Okay? And what I'm thinking, and of course, as x heads to 0, I'm sorry, delta x heads to 0, you know, part of this limit thing over here. In fact, look, if I want this relationship, that area, I guess I could do something like say, okay, let's then replace delta big F with this stuff. F of x times delta x. And look. And now we can do the evaluating that we couldn't do before. And so there's no place to plug a 0 in for delta x, and so all I have left over is f of x equals big F prime. And so what we've just done is kind of prove something. We're kind of saying that this thing here has an area under the curve function. Okay? And this thing here has an antiderivative, big F. Big F is that area under the curve function. Well, it turns out that the derivative of big F is little f. The derivative of big F is this. Now, we came up with big F as being the area under the curve function. Big F is the area under the curve function, and then when we take the derivative of the area under the curve function, we get this. So, where am I going next with this? You know, you're feeling like, Kukla, you're just sort of rambling here. Don't worry. It'll all come together. So, when I take the derivative of big F, I get little f. If I integrate little f, I get big F. So, yeah. Nice. So now I'm thinking, well, okay, I understand then that the area under the curve function equals the integral from a to x of f of t dt. Okay? We then want to come back at this and say, well, what happens when I take the derivative of both sides of this equation? Well, let's see. The derivative with respect to x, derivative with respect to x. On the left-hand side, I get, you know, I could certainly say I get df dx, but I think big F prime. On the right-hand side, what do I get? Well, let's think about this. This is a constant, and this is a variable. In fact, it's the independent variable for this area under the curve function. Now, remember when we said that we would evaluate this integral by doing the antiderivative at each of these and then subtract. So I'm going to replace this integral. I haven't done this derivative yet. In fact, here, I'll give you this. D dx. Okay. So I take the derivative over here, and I know that this black integral is this with the antiderivative. So now what happens when I come and I take the derivative? Well, look, the derivative of big F, we know that's called big F prime. The derivative of big F evaluated at a point. Big F evaluated at a point isn't a function anymore. It's a number. It's a y value on the big F graph. If I take the derivative of that number, I get 0. And so look, what I'm saying here, what I'm seeing here is, yeah, when I take the derivative of this integral, the derivative of this integral, I'm getting big F. And a few moments ago, what did I say? When I take the derivative of big F, I get little f. So I can now understand this. Now, almost there. It's kind of thrilling. Here's little f. So, here's what I want you to recognize. When I took the derivative of this integral, I got little f. Well, what must be the relationship between these two actions, the integrating action and the derivative action, if the result of doing both of them is little f? And the answer is just like plasma grenade and shield, they undo each other. They undo each other. So when I take the derivative of the integral, they undo each other. And poor little Space Marine is sitting here with no shield anymore. All right. So, but wait, there's more. No, not that. I want this. So, what we're talking about here is the fundamental theorem of calculus. And actually, the fundamental theorem of calculus comes in two parts. One of those parts is the part that we've already discussed and used. That is that if I have the integral from a to b of little f, that's going to be the same as big F of b minus big F of a. This is the antiderivative of that. So where big F prime equals little f. This thing that we talked about before is a method of using the antiderivative to evaluate the integral of this function using the antiderivative. All right, I'll say it. If this is velocity, this is position. I'm using the antiderivative of whatever this function is, and I'm evaluating not by computing the area under this curve, but instead by saying, I just want to change in y values over here with this antiderivative function. Okay? So this is FTC, Fundamental Theorem of Calculus, Part 2. And we'll use it a whole lot. I just mean almost every day for the rest of the year, you're going to be using FTC2 because FTC2 is what we use to evaluate integrals with. Now, granted, in an earlier video, I said, hey, we could appeal to the geometry of the situation to evaluate that integral. And I sure can, and I sure will. This, though, will be much more common. This will be, we use this every day. So please make sure you're clear on FTC2, the second part of the fundamental theorem of calculus. There's an FTC1, and it's something we just showed. FTC1 is all about taking the derivative of an integral. Okay? So I have this situation. I have y equals the integral from 4 to x of sine t dt. In fact, let's go with that. Okay, so here's a function. And my function is this integral. Or my function is the area under the curve function. When I start at 4, when I keep sine as that function as a constant, and the area under the curve depends on how far over I go. But what did we just see about taking the derivative of both sides? When I take the derivative over here, I get big F prime. But what did we see happen when we took the derivative of this integral? Do you remember? When we took the derivative of the integral, derivative undid integral, and I was left with sine x. Now, let's talk about sine x versus sine t. Some people are a little like, what's up with that? So let's address that issue. All right. Remember how I said that the integral of this was going to be the antiderivative evaluated between these two places? So the antiderivative of this is negative cosine t, and I want to evaluate from 4 to x. So what's that going to be? Well, that's going to be negative cosine, I'm plugging this in, minus negative cosine this. Yeah? So that's just this integral part. What I want to do now is I want to take the derivative with respect to x of negative cosine x plus cosine of 4. Right? Well, tell me, the derivative of negative cosine? What is the derivative of negative cosine? The derivative of negative cosine is sine. I'm taking the derivative with respect to x. So even if I'm thinking, chain rule, this is just going to be when I take the derivative of the inside, dx, with respect to x. Now my plus sign. And here, cosine of 4, that's a number. And the derivative of a number is 0. So look what happened here, right? I wanted to take the derivative of this. When I was done taking the derivative of that, I got that. Sine x, not sine t. Okay? That's why this is a dummy variable. It's not like anything we ever care about. How far over we go. And so what I want to say is that when I take the derivative of an integral, they undo each other. But many students say, well, Mr. Huga, where did the t go and how did the x get there? Well, this is where the t went and how the x got there. But the casual student wants a thing. And so here's your thing. When you take the derivative of an integral, they undo each other and this falls here. I know. Really. But it works. I've seen so many kids who just like, yeah, I see it, but my brain isn't letting me own it. And so we're just going to go to the place where we say FTC1 is all about taking the derivative of an integral. When I take the derivative of the integral, they undo each other, and this comes here. There. That's FTC1. Now, things do get a little more interesting. First, please note that that always has to be a constant. So if I have something like this, the integral from x to 4 of sine t dt, and I want to take the derivative of this with respect to x, yeah, I got a problem, because the thing that I proved this morning on this video was that from a constant to x. So I really need my constant down here. And that's okay, because I know my integral properties. I can switch these if I put a minus there. Okay? So don't forget your integral property. And what's that going to do here? Well, what I know is that the integral from x to 4 because we already talked about that with the integral properties. Yeah, I'm going to switch these and be 4 to x, but have a minus there. And so when I take the derivative here, when I take the derivative of this integral, that minus is still going to show up. But now I'm going to have minus sine x, right? Because that one goes in there. But this minus is now here because I flipped these guys. Okay, hold on. Take it a little further. So what if I have this? 4 through x squared of sine t dt. Well, again, if I want to take the derivative of this, derivative undoes integral, this falls in here. So I've got sine of x squared. But wait, remember, we're doing the derivative with respect to x. I still need to take the derivative of the inside. Yep. Don't forget chain rule. This is a place where a lot of students make a mistake. I'll say more often, though, that the forgetting the chain rule mistake is forgetting FTC1. Because we use FTC2 all the time, and only occasionally use FTC1, how do I take the derivative of an integral? People forget all about this process. So you might want to do a little highlighter box around this. Okay, so what happens, in fact, why don't you do one of these? The integral from negative 2 to 3x of secant t dt. Okay, here's y. I would like you to find dy dx. Please find dy dx. Okay, so what'd you get? Did you take derivative of integral? Did derivative undo integral and this fall into here for secant 3x? Did you remember to take the derivative of the inside function? That's it. There's our derivative of this integral. I feel like you want one more. Here, have one more. Y equals the integral from 2 to x squared plus 2x. Yeah, why not? Square root of t dt. Go ahead, take the derivative. I want the derivative with respect to x, please. All right, well, what do you think? Here's what I think. I think derivative undoes integral, and this goes in here. Square root x squared plus 2x. But because I know the chain rule, I have to take the derivative of the inside function. 2x plus 2. There it is. That's the result. That's FTC1. FTC1 is all about the derivative of an integral. Then, we can prove it. Again, it's not a big deal. If I have big F equals the integral from 4 to x squared of sine t dt, I can use FTC2 here to say that, okay, well, this integral is going to be the antiderivative of this, negative cosine, evaluated here, minus negative cosine evaluated here. Okay? So this is big F of x. And sure, I could tidy that up. Now, I want to take the derivative of both sides of this equation. So here I come. Let's go derivative with respect to x. Taking the derivative of both sides. Over here, I get big F prime. And over here, what happens? I'm taking the derivative of this function. Well, the derivative of negative cosine is sine. Leave the inside alone. Now come back and take the derivative of the inside function. Plus the derivative of cosine of 4. Cosine of 4 is a number. The derivative of a number is 0. So look what I got. When I take the derivative of both sides of this equation, I get sine of that thing times the derivative of that thing. So rather than have to go to this step where you find that antiderivative and you set up this FTC part 2 thing and then come and take the derivative, I would much prefer you to understand that when I take the derivative of both sides, derivative undoes integral, this falls in there, and don't forget chain rule. Okay? The last thing I want to say about FTC part 1 is this. FTC part 1 depends on a constant to how far over I go. These cannot be that. If I do, if I make these x's and this x, no, now I'm changing my function as well. No, 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 don't want to be changing the function. I just want a dummy variable here. Okay. This is big F of x. Fabulous. So, this, in order to do that FTC1, take the derivative of both sides thing, this has to be a constant. And that's my variable up there. So, what if we have this? x squared, 3x, f of t dt. No constant. And so what I need to do is create a constant space here. So I'm thinking about, hey, there's this function, and I'm going from this place called x squared to this other place called 3x, and I'm finding the area under that curve. That's what this integral is all about. I understand you want the squared thing to be bigger, but it's not. Sorry. Just, imagine that x equals 1/2. So 1/2 squared is 1/4, and 3 times 1/2 is 3/2. There, see? 3x can be bigger than x squared. So breathe with that, and we'll get through this. But I do need a constant in order to use FTC1. So let's say I'm going to go to this place called B. And if you want, you can certainly call it A or C. So you're going to go to some place. And I'm going to take this integral, and I'm going to rewrite it as two separate integrals. I'm going to say, well, the area under the curve from here to here, so x squared to a of f of t dt, plus the integral from here to here, a to 3x, f of t dt. Okay? So I'm splitting this one integral into two separate ones. And this is actually using one of those integral properties we talked about in that earlier video. But remember, I can't go from a variable to a constant. I really need to go from a constant to a variable. So I'm going to rewrite this as negative integral a to x squared, f of t dt. And don't forget we've got this positive thing here, a to 3x, f of t dt. And so now when I want to imagine, hey, this is big F, and I want to imagine taking the derivative of both sides here, I got to take the derivative of this, and we know that's going to be f of 3x times 3 minus the derivative of this, which is going to be f of x squared times the derivative of the inside, 2x. Okay? So this is what I get when I take the derivative, but both bounds are variables. I have no constant present. And so I think it would be really good for you to do one or two of these, otherwise you're just going to forget. So how about this one? The integral of 2x to x to the third of square root of t dt. So this is big F of x, and what I want is big F prime. So pause the video and give me big F prime. Hey, welcome back. So remember, can't use FTC1 unless I got a constant down here. So I'm going to break this up into 2x to a of square root of t dt plus the integral from a to x to the third square root of t dt. I'm going to flip these so my constant is here. Remember, it means you have to pull out that negative. And now I'm ready to take the derivative. The derivative of this integral will be minus square root of 2x times 2 minus square root of 2x times 2. And yes, I would prefer to put the 2 out in front rather than behind so that no one thinks that that 2 is actually under that radical. And then I'm going to add to that the derivative of this one, which will be square root of x to the third times 3x squared. Yes, you can of course flip these, but no, I don't really care. And no, I'm not really going to be doing anything else than this with this. This sort of question, this specific type, where we've got these variables both on top and bottom, this is often not a free response question. This is often a multiple choice question. All right. I do think you probably need a little more practice, both in the doing and gaining confidence part of it, but also in the part where you're more likely to remember it in a couple of months when we come back and look at it again. Okay? But this is FTC Part 1, where you take the derivative of an integral. All right, and don't forget, of course, we've got FTC Part 2, right? Just because we've been spending a lot of time now talking about FTC 1 doesn't mean we don't have an FTC 2. So let's be explicit about FTC 2. I've got this integral of little f from a to x, from my constant to some place. We know that this makes big F of x plus c. Yeah, remember, functions that differ by a constant have the same derivative. When I go backwards, I always have to remember that plus c. So let's see what we can do about this. Tell me what this would be. The integral from a to a of f of t dt. What would that be? Well, yeah. Actually, on the other side, we're calling that... oh, that's what I want you to do. Okay, so what happens on the left and what happens on the right? Well, over here, I know that this integral from a to a is equal to 0. And over here, remember, big F of x, and x is that guy. So I gotta have big F of a, okay, plus c. Can we solve this equation for c? Sure. C is going to equal negative big F of a. Excellent. So let's now come back up here and let's get rid of this and replace it with that. So now this looks like big F of x minus big F of b, big F of a, and look, there it is. There's FTC2. There's our how do we evaluate an integral. The way I evaluate the integral is by using this antiderivative. This is the antiderivative of that when big F prime equals little f. Okay? So there we go, FTC2. Make sure you're comfortable with that. We'll certainly give you a lot of practice with it. Please don't forget FTC1. How do I take the derivative of an integral? Okay? I kind of want to talk a little bit about, I kind of want to do some more. All right, I'll do a little more. Thanks for your indulgence. I mean, it's a little longer video this time as opposed to 2 videos. So, I actually want to have a conversation about areas as opposed to integrals. I want to get in that direction of talking about areas. So, let's imagine that I have this graph, and this is y equals x squared minus 1. Okay? And let's call this region here, let's call that region region 1. And let's call this region here region 2. Okay? Now, if I want to find that area, well, that shouldn't be a problem, should it? Isn't it just the area under that curve? Isn't this just going to be the straight integral? Well, yeah, yes and no. Because I don't know how to do it. If I've got a curve like this and I need to find the area under that curve between the curve and the x-axis, sure, I got no problem with that. I've got this top boundary and this constant bottom boundary. And here, this bottom boundary becomes a different bottom boundary. This stays as the top boundary the whole time. Just like this stays as the top boundary the whole time. But unlike this, where the top stays the same and the bottom is always the x-axis, here the bottom changes. I have two different bottoms. So how do we figure this out? Well, there are a number of ways. One way that most students do prefer is to say, okay, I want to find the area of this, and I want to add it to the area of this. And I don't know that that's the best approach to this, but what would that look like? Well, if this is that function, this must be 1. And let's say here we're going out to 4 minus 1 is 3. Okay, so that point is 2, 3. So I could say this is two areas added together. The first one is the area of this rectangle. And the height of that rectangle is 3, and the width of that rectangle is 1. So I'm going to have 3 times 1. I appeal to the geometry of that situation, plus an integral. Now, this is a very interesting integral, and we haven't really talked about how do I do this, but this area is going to be, look, think about integral this way. Think about integral not as area, but as all these lengths. And think about summing up all these lengths. Well, what determines how long that is this number minus this number. Think about if I gave you this. How far is it from negative 1 to 2? Well, we would do 2 minus a minus 1. And we would get the distance is 3. So what I'm thinking about here is that I'm taking the number on top and subtracting the number on the bottom. I think I'm taking the number on top and subtracting the number on the bottom. I think I'm taking the number on top and subtracting the number on the bottom. And so what this integral is going to be is top minus bottom. And what does that mean in this problem? Well, it means in this problem that the top is this horizontal line, y equals 3, minus, what's the bottom? The bottom is this curve, x squared minus 1 dx. And so this region is 3 plus the integral 3 minus x squared plus 1. So how about I just say 4? 4 dx. Now what about the boundaries? Well, this integral goes from 1 to 2. Okay, and now we could use our antiderivative. Not here. This isn't an integral. We could set it up as an integral. That could be the integral from 0 to 1 of top function minus bottom function. And then now we're integrating a constant, and remember the shortcut for integral of a constant is the constant times b minus a. So I've got that, plus my antiderivative evaluated at these places. So that's going to be 4x minus x to the third over 3, evaluated from 1 to 2. All right, so what do I get? I plug that 2 in, I get 8 minus 8 thirds, minus, I plug that 1 in, 4 minus 1 third. Don't forget to distribute this negative. Don't lose this plus 3 out in front. So if we tidy this up a little further, 8 minus 4 is 4. 4 plus 3 is 7. 8 minus 8 thirds minus a minus 1 third, that's plus 1 third. So minus 8 thirds plus 1 third is minus 7 thirds. There's 21 thirds minus 7 thirds, and I get 14 thirds. So this region 1 has an area of 14 thirds. Great. But that's only one way to do it. In fact, I think that's kind of the longest way, the hardest way to do it. Other students say, well, Mr. Kukla, instead of breaking it up into those two areas, could I do this? Could I find this area and then subtract this region? You sure could. We know that coming straight down for there means this is 2. So this rectangle has a length of 2 and still has a height of 3. So region 1 could also be 2 times 3 plus, no, we're taking this part away. We have to subtract the integral from 1 to 2 of our curve. Our curve here is now the top. This 0 is the bottom. So x squared minus 1 dx. The antiderivative here, well, I'm going to have 6 minus x to the third over 3 plus x, no, that's a minus x, and I want to evaluate from 1 to 2. All right, so I plug in my 2, and I get 6 minus 8 thirds minus 2 minus, now I plug in the 1, 1 third minus 1. All right, so let's distribute. That's going to be 6 minus, I want to tidy this up first, sorry. 8 thirds minus 2 minus 1 third plus 1. So here I'm getting 7 thirds minus 1. Oh, look, there's a negative outside. So now I'm going to have 6 minus 7 thirds minus a minus is plus 1. And here I am with 7 minus 7 thirds, and we know that that's 14 thirds. To me, that's a little less labor intensive. I don't really care which one you do, okay? But you're going to have to break this into pieces to do it. What about region 2? How could you find region 2? So I can't do this. It's not x squared minus 1 dx from 0 to 1. I mean, I like the 0 to 1 boundary. Oh, wait, isn't it? Hold on. I thought the integral was the area between the curve and the x-axis. Well, so, yeah, isn't that right? However, and be careful here, however, this is below the x-axis. So if I'm talking about areas, I got kind of a problem here. If I'm talking about area as opposed to integral, I'm going to get a negative number. And like when I integrate this, I'm going to get a negative number. Why am I going to get a negative number? Well, hold on a second. Let's think about what's going on here. I told you over here that we could use top minus bottom. Let's think about top minus bottom. From 0 to 1, our top is y equals 0, minus our bottom is our curve, x squared minus 1 dx. So what's happening here? Well, that's going to go away, and I can pull that constant out. 0 to 1, x squared minus 1 dx. All right, well, what do we get for the antiderivative here? What happens when we use FTC part 2? Minus x. I evaluate the antiderivative from 0 to 1. So I'm going to have 1 third minus 1. If I plug in a 0, I get 0. And so this is minus 2 thirds. Well, that's fabulous, except that I'm talking about area. And area has to be positive. So while this integral, all this stuff here, turns out to be negative 2 thirds, a minus times a minus gives me positive 2 thirds. So region 2 has an area of 2 thirds, right? Not the integral. The integral here gives me negative 2 thirds. I'm looking for area, and the area has to be positive. All right. Wow. There's a lot of stuff to be thinking about and going on here. Okay, so that's it for this video. And I think that's it for sort of conceptual stuff for a while. I may or may not come back and try and convince you of all the stuff I went through here in the video. Again, we may just leap on to some more practice in the next video. All right, have a wonderful day, and I look forward to seeing you soon.